Hi, welcome to our second unit. That first unit was quite a long one, right? Covered so much. But the unit should get a little shorter for a while now because we've really laid the framework, the foundation for understanding and analyzing our data structures and algorithms. So we've learned what? Quite a bit of algorithms, haven't we? But we've only learned one data structure. We've studied the array and the abstract data structure, the list, and we made it with what we call an expandable array. Well, guess what? We're still going to be working on the abstract data structure list. I know. But I do have something exciting. We're going to be learning a new kind of backing data structure called a linked list. So we'll be using linked data structures for both this unit and the next unit. We're going to see some exciting things that we can do with it. So we'll start with the list, which you're already familiar with, but we'll be doing it in a unique way. So what exactly is a linked list? So linked lists, just like an array list, will grow and shrink in size dynamically as we need them to. So that as we add more stuff to it, they're going to grow. Um, an array is a data structure where uh, memory is carved out in a sequential pattern, and we can use mathematics to simply calculate basic arithmetic, really, to calculate the location of a specific item in that array. Well, a linked list is not like that. So I've got a picture of one here. So a linked list is basically you have a series of what are often called nodes, and these nodes they contain some sort of data. Okay. Now, this data could be a simple integer, or it could be a reference to a much more complicated class. It could be an enemy in a video game, or it could be a series of important information about a student, or whatever. But it's about how that the list is made. Now, so these nodes that we're going to call them quite often will have some sort of data, and that's what's important for us to get. But they need to have something else, a reference to the next node, and I'm going to typically call that next. It could be called anything, of course. Now, next is simply a reference, or back in the day we were called pointers, to another node somewhere in the memory. Now, these are not sequential. So we could not just say, okay, I know the memory address of this one. If I simply, add 32 bits, it'll take me to this one. No, not at all. This could be one place in the memory. I'm picturing, someplace far over here on the computer, and then the next node could be way over there. And the next node after that could be way back over here, and then maybe that one's over here. They're all scattered all over the place. But as long as each node contains a reference to the next one, we can navigate through the list. So let's practice doing that right quick. So imagine I've got this list of 4 items. So the way that it would start is I would make some sort of reference to this node here called first, okay? And then, so when I start my list, I can find the first item using the first reference, and then I can take first.next to go to the next item, and then I can call dot next on that to go to the next item, and dot next on that to go to the last. So, and that's pretty much how we're going to iterate through the list with a series of calls of dot next. Now, data linked lists can be doubly linked list or singly linked list. Doubly linked lists are doubly better, but they're a little more complicated, so we'll wait and do that later. A linked list that is singly linked, though, has a very good advantage, and that is it allows for O1 insertion at the front of the list. Because I have a reference to first, I can easily just simply slip a new node right here in front at O1 speed, and that is going to be super advantageous. So with an expandable array, with the array list, if you wanted to add something to the front of that list, it was really, really slow, right? You had to move everything down and index one at a time. It was the sluggish O in. We don't have to deal with that with a linked list. We get O1 insertion at the front. Now, unfortunately, inserting at the back with a singular linked list will require me starting at the front and going next, 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 and that's O in. So we're sacrificing the O1 runtime at the back to give us O1 runtime at the front. But don't worry, a doubly linked list is going to fix that as well. Okay, so Unlike an array, though, we can't just immediately access the third element. We don't get O1 runtime at a specific index because I have to iterate through all the nodes up to it. So if it's at the front of the list, I can access it super fast. If it's in the middle of the list, we're talking O in. You might say, well, isn't that O in divided by 2 if it's right in the middle because you're only going through half of them? But remember, we disregard the divide by 2. So this data structure is called a linked list using linked data. So let's go ahead and get started. Okay, so I've got a new BlueJ project. I'm calling it linked list. The Java is linked list is java.util.linklist. We're going to try and avoid some name collision, so I'm going to try and give it different names. So just keep that in mind. So linked list is the name of my project. Let's make a class and let's call it Linky List. I don't know. Sorry, Linky List, right? Or Linky Boy. We could call it int list or something like that, but we'll just start with this because we're going to make a linked list of just ints. We're not going to do generics yet, okay? Obviously, that's coming, but the important thing is the algorithms, and the generics are really just a piece of cake once you understand that. All right, so let's start. We'll open this up and Control A. I don't need that. All right, so here is my. Let me get rid of all that. Okay, so I want to have a clean slate. So let's start with what we're doing. We're making some nodes. Okay, so I've got this node here, and that's exactly what we're going to call it. We're going to call it a node, right? You remember that? And then each node is going to have a couple things. It's going to have a reference to its own personal data. So each node has its own data. That means it's an instance variable, right? Depends on the instance of node. And it's going to have a reference to next. And right now, we're going to make this node object. And let's see how we could do that. Well, in order to make an object, you have to have a class, right? The name of this class, though, is Linky List, but I need a class called node. So I'm missing the word class. So we have two options. We can make a brand new Java file called node, but then every single time we want to store something different, we have to make a different node class. And in fact, our node class is really only relevant to this linky list. So we should just make that class occur here. And the way we do that is what's called a nested class. So we're going to say private class node. Okay, that's pretty weird for most of you, right? Probably never seen a class within a class. Totally okay, though. We can make the class a static nested class, which means that that class belongs to the linky list class, or we can make node and basically an instance class, meaning that each instance of the linky list class gets its own personal node class. I don't want to get into the differences too much there, so I'm just going to leave that out and to call it private class node. But yeah, an inner class. Next, the other thing that's weird is that it's private. Well, I don't want my users seeing it in their documentation when they switch over to documentation. I don't want them having any idea that I'm doing this. They're just concerned with the list. They want to be able to add, remove, get, all that stuff. They don't even know how it's done. They may want to know the runtime operations, but they don't need to see my private parts, right? So we'll keep it private. But we'll have direct access to it from anywhere in its surrounding class. So it's private to everyone else, but it's not private to Linky List. I get to access all of these just absolutely directly. So let's make some variables. Private, we're going to be dealing with ints today to keep it simple. And private. Now, the next, what is this next going to reference? It's going to when we create this list, it's going to reference the next node in the list. So what is the next node? What is its type? You remember, everything in Java has to be strongly typed, and it is going to be of type node. So that's kind of weird, right? We have class node that has a variable of itself, right? That's that linked nature, though, that we're linking it to itself. Or excuse me, to another instance of its of the class. But remember, each node is going to reference some other node, so it's totally okay. Let's make it a constructor. My constructor, all I need is the data. Okay, I don't need let's call it D. I don't need to have what the next is, because whenever we create a node, let's just imagine it's the very first node in our list. The very first node is actually going to point to nothing, right? Because until there's something else to reference, the node reference will be null. So data is going to get the value D, and next is going to be pointed to null. Now we can directly change next. It's just going to be through a dot operator, so this won't be null for long, but when we create it, we want it null. Okay, now that's it. That's all we need for the node class. We could make methods like methods for fixing the next or changing next, but I think it's actually going to make more sense and be worthwhile for you to see how we do it through the variable names. I usually do like to do everything through methods, but I think for our purposes here today, it will actually it'll be worthwhile to see this. All right, let's make a variable for the size of my list. So size, right? Let's make another variable called first. So it'll be a reference to a node called first. So at creation, I'm not going to have that, right? I'm just going to have some node. Excuse me. I'm just going to have some node class inside, and first is going to reference null. So we're going to make, let's not even have this yet. So we've got the node class, but let's talk about what happens now when you make the linked list. So we're going to have a size of 0, and we're going to have some reference to first. Now remember, these are objects. First is not going to be a node. It's going to be a reference to a node. Super important as we're dealing with linked data that you see that. So right now it's just pointing to nothing, to null. Why? Because there's nothing in our list, right? It'll point eventually to the first node in our list. So let's make the constructor. Public linky list, and we're not going to have any kind of like default initial capacity because this is actually going to grow perfectly as we do it. So the initial size of my list is 0. When you create the list, it's got nothing in it. My first, what did I say it's going to point to? Null. Turns out I could have left this constructor blank because the default constructor for Java, they make it for you, sets this to 0, sets that to null. Those are the default values for int and objects. But I like to be explicit, so let's do that. Okay, well, we've got a linked list that you can't add to. So let's add to our list. We want it to be public, and let's go ahead and call it add first, so that people know they're adding to the front. So we'll say public void add. We can say add the front, or I'll just say add first. All right, so let's go over how we're going to do that. We're finally ready to do that. I think it's easier to understand if you picture it when the list has already been started, and then we'll look at what it's like when there is nothing in the list at all. So I'm going to make some nodes here. I got that node, and I got that node. Now I'm drawing them as if they're right next to each other, but please keep in mind they could be all over the place in the memory of your computer. That has nothing, that's not at all that way. So I've got data in this first thing here, and I've got a reference to next. So I've got some variable here called first, right? And this first is a reference. It's a set of instructions on how to go into the memory of the computer and find it. So first is going to go right there, and then next is going to go over here to this other guy. And so that's data. Again, that's a different data. And it also has a reference called next, and it's going to point over to here and might wander around a bit and come over to there, right? And So there we are and this one has data, and it also has a reference to the next node. But this is let's say this is the last node in our list. Well, then what does this point to? Well, it points to nothing. It points to null, right? Nothing, absolutely nothing, because it's the last node in our list. So now here we are ready to add, right? So what we're going to do is we're going to create a temporary node. I'll do it in green so we can see it's different, and I don't know where it'll be, right? I mean, it could be anywhere in the memory, but we'll just put it there, okay? And it's going to have some data, so when we make this, oh, I'm still in oval mode. So when we make this node, we'll know the data we want, and remember that our constructor for a node has next to null. So this will be pointed to absolutely nothing, right? So that's the first thing we're going to do is we're going to create this node. Right now, we've got to we make the node, now we've got to put it in the list. Well, if it's going to be in the list, at the front of my list, what should next point to? Well, next should point to this first node, right? So we're going to use this variable first. We're going to take its reference. Now, its reference is actually a 32-bit integer. That's what it is. It is a reference. It's a set of instructions. It's not that the node is located in the variable first, because that's only primitive. Objects are stored by reference. So we're going to copy this reference called first. We're going to copy it over to this new node's next. So when I do that, that's going to cause next to also point it. So now we've got two ways to access what will be our second variable, our second node in our list. First is still pointed there. Next of my new node, my temporary node, is pointed to it as well. That's kind of confusing. It made it look like I was pointing to its next. There it goes. So we need to fix that. Well, this first no longer needs to point there anymore, right? So we will change that reference and we'll point it to whatever temporary reference I've made to this new node. And so now, voila, I have made a new node at the front. How many steps is that? Well, first we had to make the node, then I had to connect its next, then I had to connect its first, and then last thing we're going to do is we're going to increase the size. The size was 3, and that'll become 4, right? So that's like 4 steps, right? That's O1. So we're adding to the front of a list with O1. That's something we never could do with our array list, could we? All right, so let's do it. Let's go through but before you write it, let's make some comments about what steps we need to take. So first, you need to make a temporary node, right? Oh, you know what? Public first, add first. We need to have the data that we're going to be making. Yeah, they need to tell us the data. So there we go, with data. Okay. Then what I want you to do is I want you to point the temporary node's next reference to first. How do we do that? Well, it's as simple as this. Say you had the node was called, I don't know, temp. And temp.next, you get to write right over it with that assignment. Just use that assignment operator, okay? Then what we need to do is we need to reassign the reference first to point to our temporary node, the new node that we're adding, right? Because we're adding it to the front. And then don't forget to increase the size. All right? Pause the video. You do it. I don't want you having to just watch me code and then memorize. You can do this, all right? Remember, it's you make the node and it's .next or .data to access it, all right? Its parts. All right, let's see how you did. First thing you need to do is make a temporary node. Boom. Node temp equals new node data. Piece of cake, right? Right now, the data has been set to data, the one that the user's adding, and its next is referencing null. But I want its next to reference what first used to reference. So I'm going to copy over the instructions. So temp.next is remember, it's a set of instructions to the computer where to dig out in your memory and find that node. And I want the instructions that are currently written down here, right? Remember, we type it as a node, but it's a reference. It's a set of instructions to find that first node. I want to copy those instructions over to this node I'm going to add's next reference. but I'm adding to the front. So I need to make first point to temp. Remember, temp is also, it's temporary because I made it inside this method, but it is a reference to some new node I made. So I need to make first have that reference. And please don't forget to increase your size. And there we go. All right. We are, I'm just going to erase these comments. You keep yours if you need it for study or whatever. Let's get rid of all that. And let's give it a try. So I'm going to make a new linky list. And, well, you know what? I did not make a get size method. So I really don't have the size method. I probably should have made that. We can inspect it, though. You can see that private linky list dot node. So when you make a nested class, it describes the class as the surrounding class dot the inner class. So linky list dot node is what they're going to call node. First, it's null, and the size is 0. No big deal. Let's add. Let's add the number 7. All right, let's add the number 9. Let's add the number 11. Feeling odd today. 13. All right. Let's inspect. Okay. First is no longer null. We do have a size of 4. So what is this going to reference? Well, let's find out. Let's click on it. Well, you know what? I think if you hit inspect, I think it brings it bigger. Yeah, that's a little shortcut. All right, now it's resized. Okay, this is not size. This is the data. The last thing I added, right, was a 13, and it has a reference to next. Boom, 11. Oh, come on. You're gonna make it small? Make it big. There we go. Oh. I'm trying to make it to where we can see everything. So that was the size. That's our first, right? You can see it's called first right there. Next. Next. Oh, but that one's null. Can't go any further than that, can I? Right? So 13, 11, 9, 7. Let's add 99. Yeah, all these are no longer of relevance anymore, so I should have closed them probably first. But I just want to see that it did, in fact, add. Let's go to inspect, and let's see where that little reference is going now. There it is, 99. But we didn't lose the rest of our list. It's still there. We just have to go through it like this, one at a time, right? So how would I find, like, the fourth element of my list, right? I got 0, 1, 2, 3. Well, I tell you, let's say, how would I find something at index 3? Well, if it was an array list, I would say, like, get 3, and there it is, right? Because you can just go directly there. But with a linked list, if I want to find the third element, I got to go, okay, let me go there. That's 1. That's 2. That's 3, which is actually index 2. That would be index 3. So you see, I got to go through each one at a time. Very slow, O-N, right? That's the only way to do it. Okay, let's do, so that's the algorithm for adding to the front of the list. Let's go and do a different one. Let's write remove. Yeah, let's go ahead and remove. I think I'm looking at what I need here. I never went over, though, actually, what happens when you add to the front of a linked list that is empty. Well, let's make sure that we cover that. If you probably noticed that it must work, because I didn't my code worked and I never did anything special about it. We don't have to do a special case. So in the case where your list is empty, so I'm adding this green node here, right? Well, when the list is empty, what does this point to? Well, this points to null, right? Well, the last element in your list should have a next that points to null. So I tell next to point to null as well. All right. We will see that that's not always going to be the case with these. As we get to more complicated linked data structures, we're going to have to do some different stuff. But for now, that's all we have to do. Okay. So I think we're ready for our next method, y'all. Let's do it. So we're going to remove from the front. Now, what would removing from the back be like? Well, it'd be slow, right? But from the front, 01. let's make sure we make that comment there. I'll make it a Java doc here. Um, adds to front of list. Um, let's make this 01, super fast, right? Okay, public. We're going to remove and let's return the data. So we're storing ints in this list. So we'll put a public int for the return type. And let's call remove first. All right, and we don't need a parameter since we already know we're just removing first. Okay. And this should be 01 as well. So let's talk about how to do that now. I'm going to go back to, let's see if I can't bring this up to where it was. Yeah, that's good. So here we are. Here's our situation. We got a list of size 3. It doesn't particularly matter right now. Let's deal with how many there are, but we're just going to assume that it does have something in it. Okay. So first is pointed right here. We're going to remove it, right? So what I want to do, first of all, is get a reference to that data. So let's say like int D, that needs to be this data. Okay, so we're going to grab the data that's at first. We're going to put it right there because we need to return that. And then how do we remove this? Well, I don't want this pointing here anymore. I want it pointing there. So now at this moment, I've got this node here that is got a next that's pointing to this second node. And then I've got a reference called first that's pointing to it. So question is, what happens to this node? Well, some programming languages give you a lot of control over memory. Java is not one of those. It has what's called a garbage collector. And I pictured the garbage collector looking a lot like the Wall-E robot. And so Wall-E's going to come around and it's going to look for things that have no reference. So it's just kind of wandering around while your program's running, and it's going to come across this node here. And it's going to say, where are your references? First doesn't reference you. There's no next. There's no other nodes next that references you. Nothing references you. I am going to just erase you. Or more accurately, I will free up that space in the memory to be written over somewhere else. So the garbage collector is just going to remove it for us. But it's effectively gone to us anyway, because I don't know how quickly that happens, but as soon as I move first, I have no reference to it. I have no way I could find it anyway. I don't, unless I wrote down like somehow a hexadecimal memory location, which is something Java would even let you do. So yeah, it's gone. The only thing I have is an int variable for its data, which I then return after decreasing the size. So let's go over the steps for that. So how do we move first? Get a copy of the first node's data, because we need to return. We'll return that. Then what I want you to do is I want you to point first to the second item. Well, maybe. Hold on about that. And then we'll return that the data that we had. But what if there is no node here at all? So what if somebody called? Let's just look at a couple situations actually. What if somebody called remove first, and all there is one node? It turns out that's not a problem at all, because that node here next is pointing to null, and we'll just be taking first to null, making our list empty, which is fine. But what if somebody calls remove first on nothing? There's absolutely nothing in the list at all. Well, in reality, it should do what? I mean, like what should you? If somebody tries to remove something that's not there, what should Java do? Well, it should throw an exception, right? Um, which exception should it be? I don't know. We'd have to look at. We could look at the list. Let's do that actually. Let's pull up the documentation for list. We're going that way anyway, right? So I'm just gonna say Java API. I like the 9. It's got a search bar, but it's also got Java effects. So let's go in. Let's go in the list. We're going to be implementing lists at some point, so we might as well do this now. Java.util.list. What happens when you try and remove something that's not there? Well, we could get an index out of bounds exception, right? Let's see here. Yeah, index out of bounds exception. Well, actually, you know what? We're not just going to be doing lists, though. We are going to be doing something else. Linked list actually implements a couple of different interfaces because you'll notice that it also does something called a queue. So let's take a look at what happens with queue. So, well, we could return a special value means null. What does this remove? No such element exception. That's good. Let's do that. Let's do that. So that's going to be our special case. If the node is empty, by the way, we need to add that to our list. Let's decrease size, right? So we're gonna add that first things first. If list is empty, throw no such element exception. It's all one word, of course, camel cased. It's an instance of a class. Exceptions are instances of classes. No such element exception. Is that java.util? It is. It's java.util. So either import it or just use its full name. I'll probably just use its full name. All right, write that code. Pause the video and do it, please. Okay, here we go. If size is equal to 0, throw new java.util.no such element exception. List is empty. We could. There is actually some methods that we could do where it returns null if it doesn't remove, or something like that. But I like that. No, let's stick with that term for now. Get a copy of the first node's data to return. Okay, cool. So int d is equal to first data. So I just got a copy of it because I'm about to erase it. I want to make sure I have that so I can return it to the user. Because that's just typical. When you remove, typically you return what was there. Point first to the second node. So first is going to go to what? Okay, how do I do this? What's the second node? First dot next. Right? Did you think about that? So we got to point first to first dot next. And decrease the size. And we'll return the data. All right, before we go any further, though, I do want to go ahead and write that method for size. It's bothering me that I don't have it. All right, let's try it out, y'all. Okay, class compiled. That's always a good sign. New linked list. Boom. Let's add 7, 9, 11, 13. Okay, we got our list here. We got 13, 11, 9. Perfect. We're doing good. Now, I want to remove. We return to 13, which is the last element I added. So the last one I add is the first one out, right? Okay, that looks pretty good. Let's take a look at the size. 3. Let's remove. It removes the 11. Check the size. 2. And it should still work. I mean, we should still have all of our references. There's our 9, there's our 7, and then that's null. Bingo. Okay. Let me see. We want to make sure I cover all the methods that we need in this. You know what? We got to traverse. So if we're going to traverse the list, what would we... Let's make a 2-string. Yeah, let's do that. ToString is a method that every class inherits. Remember, every class, whether you say so or not, will subclass the class object. And the class object has several methods in there, one of which is called toString. So let's make a toString, public string toString, and let's do that. So we're going to loop through. We're not loop. We're going to iterate through each one of these. I keep using the word iterate, and I don't mean to scare you about iterators, but yes, they will come. But we're going to iterate. Let's just do this one by hand. So the way that we're going to do this is we're going to create a reference that I usually call current. And we're going to start it first. And what we're going to do is we're going to keep looping while the node current is not null. And as long as it's not null, we're going to do some things. We're going to add its data to our string that we're going to return. And then we're going to set current to the next node. So again, I'd like to, if you'll bear with me one more time, we can maybe take a look at what that's going to look like together here. So we've got first, right? That's really all we have. We got first and size, right? That's all we have directly referenced. And I am going to iterate through with my toString. So I need to make something to return, maybe call it str or to return. And, I don't know how fancy you want to give it this. You could add a little, Java usually has a bracket to start with and yada, yada, yada. But we can grow to that. But for now, let's just add the data and a comma, okay? So this is my data and this is next, right? So I need to create a reference though, and I'm going to create a reference called current. Current is going to point to what first points to. So you can imagine how that's going to happen, right? I'm going to get the reference first as and make current point to it. And so then current.data is going to go right here. I'm going to add it to the string and then maybe put a space or comma. We'll put a space. Then what does current need to do? Well, current needs to go to what next is pointing to, right? So current needs to become current dot next, and that's the way that's going to look. You're going to say current, my reference current needs to now get the reference that is located in its current dot next, and we're going to keep doing that, and then copying the data, and then we're going to do current dot next until current ends up pointing to null. Once current equals null, we are done. So can you do it? Can you just write that right quick, the toString? I'll leave this up here as a reference for you to look at and think about. Give it a try. Okay, let's see how you did. Node current is going to be first. String str is going to start here. And I'm going to say while current does not equal null. Oops. Need parentheses around that. So what will we do? Well, current does not equal null. If I'm sitting on a node and it's not null, let's add to string. We're going to add current.data. And it might need a quote there since you're adding. I'm not sure, but I'll just do that just to make sure that it knows that I need to make my data into a string. If it was an object, I would say current.data.toString. I'd call the data's toString. Okay, so string is going to add in current.data, and then let's do current. We need to make current advance forward in the list, so we'll say current equals current.next. When we're all done with that, we will simply return str. Oh, you know what though? I wanted there to be a space, so let's do that. All right, I'll compile. It didn't get mad at me. That's always a good sign. So let's add some things. I've been doing a lot of odds lately. How about some evens? 4, 6, 8, 10. toString. 10, 8, 6, 4 in reverse order, right? Because we are adding to the front. All right, that is all for this, but I want to summarize some things that we have discussed, okay? So let's just summarize. By summarize, I mean what were the methods we did, the operations that we've done, and what were their O1 times. So we are able to add to the front of a linked list in O1 time. How long does it take to add to the front of an array list? O in, right? You have to iterate through the entire array and shove everything back one. It's awful. How about removing from the front? Boom. O1 as well. All we did was make a reference to the data that was there, and we said, hey, first, don't point to this node, point to that node. Took like 3 steps of code, no looping, no shifting. What about an array list? You move from the front, you got to take everything from index 1 to the end and shift it down 1. That loops through the whole thing. Slow. What about the traverse the list? Well, you're traversing a list, right? It's going to be O in, going to be O in for both, right? So that's pretty cool, right? Some fast stuff. There are some shortcomings to the linked list, of course. Sometimes array list is better. Sometimes linked list is better, and we'll discuss that as we go forward. So in our next lesson, I look forward to sharing with you more operations that we can do. So take care.